Hey everyone, today we're going to talk about the central limit theorem. This theorem is one of the most important theorems in statistics. Remember that in our previous video, we've talked about the sampling distribution of sample means, and we've also talked about sample and population. We've learned that the sample is drawn from the population. Now, we are not always sure if the sample drawn is normally distributed or not. However, the central limit theorem can be used to determine if the sample is normally distributed or not. Now, the central limit theorem states that if a sample has a large enough size, it will have a normal distribution or have an approximate normal distribution. So this theorem immediately guarantees to us that if our sample size is large enough, then that particular sample, is normally distributed no matter what. So the sampling distribution of sample means is approximately normal when the size of the sample is greater than or equal to 30. So if our size of the sample is greater than or equal to 30, it guarantees that our sample is approximately normal. So whatever the mean of that sample, that would be the mean of the population. And the standard deviation is the population standard deviation divided by the square root of the sample. So it immediately guarantees us that the population mean is equal to the sample mean because the sample is approximately normal because of the central limit theorem. Let's have an example here. So a population of size n is equal to 100 has a mean of population mean is equal to 30 and a standard deviation of 5. So this is the population standard deviation, which is equal to 5. What's the probability that a random sample of size n equals 30, so this is the sample size of 30, will have a mean of 35 or more? So what we're going to do here is we're going to make use of the z-score. But before we get to use the z-score, we have to determine first the sample standard deviation. We know the sample mean already. We're looking for a sample mean of 35 or more. We have to know first the sample standard deviation so that we can use the z-score formula, since we are going to determine the probability of that random sample. So first, since we know the the population size, and we also know the population mean and the population standard deviation, we are going to make use of this formula. The sample standard deviation is equal to the population standard deviation divided by the square root of the sample size times the population correction factor. So we are going to take this. And after that, let's copy this one right here. Note that the population standard deviation is 5 and the sample size is 30. The population n is 100 and the sample size is 30 and the population is n equals 100, so that's 100. So let's solve for this. So we have here 5 and 30. Let's use our calculator later. Let's compute for this one first. 100 minus 30 is 70 and 100 minus 1 is 99. So let's compute for this. If you have a calculator which you can use to compute this immediately, you may do so. But for now, we're going to manually calculate for this one using the calculator here in our computer. So there. So first off, we have 5 divided by the square root of 30. Oh, where's the square root? Right here. So that's 5.4772. I would advise that whatever you got on your calculator, do not round it off. Okay? So, however, in our case here, it's quite lengthy. So, I'll just go into... Actually, get all of that. Get all of that. But I'll only take this part here. But for you, please do obtain all the digits for the computation so that we can retain the actual computation. For the next one, we have 70 divided by 99 and take the square root of that one. this number right here. Let's paste it, and I'll just get, I guess, this part here. So let's have this one. Now that's 5.477225575 times 0.840.8749651. That's 4 points and something. So let's round it off. Let me take this here. That's 4.61. 4.61. So our sample standard deviation is 4.61. From here, let's get the z-score so that we can use this normal curve here to determine the probability of the particular sample mean. Remember that we can use this normal curve since the central limit theorem tells us that this particular problem is approximately normal since the sample size is 30. Take note that it's approximately normal if the sample size is 30 or above. Okay, so let's take this z-score here. So the sample mean is 35. It's right here, 35. Take this out, 35, and the sample. The population mean is 30, and the sample standard deviation is 4.61. So let's compute for the value of the z. So that is 35 minus 30. That's 5 divided by 4.61. That's 1 point something. Let's round it off as 1.08. 1.08, let's say that it's somewhere right here. Let's have our pen here. Right here. If this is our population mean, or rather the z equals 0, then 1.08 should be somewhere here. 1.08. And take note, what we're solving is this area right here, a mean of 35 or more than, so more than that, 35 and above. So what we're looking for is that area in red. So what we're going to do is we get this area first, the area in blue, then subtract it with 0.5, just like what we've been doing with the areas under the normal curve. So let's take 1.08. 1.08 is right here. 1.08, that's 0.3599. So what we're going to have here is, have this one right here. So 0.5 minus, what was that again? 1.08, that's 0.3599. 0.3599. So let's subtract that. 0.5 minus 0.3599. Was that correct? Yes. So 0.1401. 0.1401. So the probability is 14.01%. So that's the probability that the sample size has a mean of 35 or more than. So basically, that's how we use the central limit theorem. It just guarantees us that a particular sample is approximately normal if the sample size is 30 or more than. So I hope you guys learned a lot today. For our next video, we're going to have the word problems involving sampling distribution and sample mean. So thank you guys for watching, and see you guys on the next video.